Today I want to implement tail calls. So my language Plum doesn't have loops, so instead you use recursive functions, which is common in functional languages. For example, this square root function has this square root recursive function that calls itself. It has this candidate of what could the square root be. It starts with 0, and then it increments that until that candidate is larger than that the candidate squared is larger than the target. It's not super efficient. I know there are more efficient ways, instead of linearly searching through all integers and checking if that's the square root. But the point I'm trying to make is that this function is recursive instead of what you would usually write as a loop. And that means that on the stack we have quite deep function calls. If you calculate the square root of a big number, then you will have a couple of these square root recursive functions on the stack. You have square root recursive that calls itself, that calls itself, that calls itself, and at some point, we find the correct value, and then we return and return and return and return. So it really is, it's kind of recursive. So I want to fix some properties of that, because a side effect of this being recursive, or an unintended effect, is that this can stack overflow for big numbers, which a loop can't. And this is especially important if you use recursion for, iterating over giant lists or calculating giant numbers, or for a loop it's no problem executing like 1,000,000 times. But for these kind of recursive functions, the stack is kind of a limit. And also, if you think about it, it's kind of weird that the stack basically stores, we call this function, and then we call this function, and then we call this function. At one time, when you've found the solution and you want to return, well, the parent function, if that just returns and returns and returns and returns and returns, why don't you even store all of these, all of these addresses, all of these things on the call stack? So what many functional languages do is something called tail call elimination, where if the last statement of a function is a call to some other function, rather than actually emitting a call instruction and pushing the current function instruction pointer onto the stack and calling that other function, which then returns to us so that we can then return to our parent, we instead just prepare the stack, and then we jump to that function immediately. That means when that function returns, it doesn't even return to our function anymore. Instead, it returns to our parent, which is fine if that function call is the last thing that we want to do. Yeah, so I want to do that. So let's maybe call the square root function, and then just as an example, square root of 16. And let's print that, which looks like this. Print the square root of 16 and format it, of course, because this is an int. And then we exit that. Currently that looks like, not like this, because we haven't imported the square root function. I hope that's available, the function. Yeah. But there is no format function. That is kind of weird, but sure. Okay, yeah. So the square root of 16 is 4, which is what we expected. But let's print the instructions being executed, maybe. Yeah. I mean, that's gonna be a lot of instructions, I think. I'm afraid. Let's see. Instruction, and let's maybe not print the data stack. Does it? Oh, and here it prints the opcode. Sure. Building the VM and then running that again, and you can see that there are a lot of instructions being executed. Like a lot of instructions. 500 something. Yeah, that's okay. Hang on, did that reset at some point? Oh, I see, after printing the file. I see. All right, so we have about 1,000 instructions for that. Yeah. Let's maybe simplify that. Let's maybe not print that. Let's just calculate that and do nothing with that. I think that's not... Yeah, that still gets calculated. That doesn't get optimized away. Not entirely sure. Oh, that's quite a bit shorter. I don't know. I don't exactly know what's going on here. But A2 is, you know, multiplication. Okay, so there's something happening. Hang on. And you can see that in here, we have a long chain of, hang on. F5 is the return instruction. So we do this return instruction, and then, you know, I think this is a jump, and then cleaning up the stack, and then we return again. Boom, boom, and then we return again. And then we return again. So there's basically the square root function uses the stack, and then when we found the square root, we just return and return and return and return, instead of just returning once. So that's what I want to change. To do that, let's look at the kind of intermediate stage here. So plum dogma, exactly. And then let's print the last compiler stage optimized. Yeah, and maybe also the instructions, because why not? How many instructions are those? 500. Yeah, okay. 500 bytes. Less instructions. All right. So, quite short actually. So the main function, it calls the square root function with 16. Makes sense. And here's the square root function. It compares something to 0. All right. Yeah, you know, it adds 1 and then it adds 1 again. Hang on, what's going on here? We add 0 and 1. It should just be 1, right? And it should be 1 as well. There should be 1. And then we subtract 1 and the argument. That's weird. Well, okay. probably, I mean, it does the correct thing, so who am I to judge, right? Yeah. Anyways, in some case it calls itself recursively. That's fine. I like that. But in here, in the bytecode, 80 instructions. That's fine. We have this call of, so we start at the beginning. This is the main function. We call square root with 16. So we push a 16 to the stack, then we call instruction number 31, which is down here, which I don't get this, to be honest. It has 1 and 1 and multiplies them to 1. Pushes the arguments, subtracts them, compares them. And then it has this jump table. Let's have a look at the square root instruction. Okay, look, initially the candidate is 0. I get that. Oh, I think this was inlined, that the first time of that was inlined up here. Or something like that. I see. So equal, greater, and less. Less is the interesting part, 48. That's down here. Here we just push 0 and 1 and add them again. Okay. And we add 1 again, giving us 2. Alright. And then a 1. Two multiplied to 4, and then we have another jump table. And then this is the interesting part, call 6. Alright, so I think this is the actual, yeah, this is the actual square root function in here. Alright. Yeah, we push the number. That seems fair enough. We push a 1, we add 1. Sure. We push the number again, push 1 again, add it again, I guess, and then we multiply that. That's basically this right here. Candidate plus 1 times candidate plus 1. And then we compare that to the target. So what we do is we push that number. Okay, this is the target. We subtract that, we compare that difference to 0, and if that's greater, or if that's less, yeah, then what we do is we push our candidate here. We add 1, we push our target, and then we call self-scan. And this call right here, that calls this function recursively, and afterwards, when that is finished, we just jump down here to 29, boom, where we pop some stuff and then we return as well. So after calling this other function, we basically don't do anything. We just jump around, clean up the stack, and then we return. So what if we did this before, cleaning up the stack, and then jumping directly to ourselves? essentially turning this into like a tight loop in the bytecode that kind of goes from here to here, then it runs through, and then boom, it jumps to the top again. Essentially turning this into an actual loop in the assembly, even though it is modeled as a recursive function. Yeah, that's the idea behind tail call optimization. It is quite efficient if it works. And yeah, let's do that. So up until this point, this kind of layouted compiler stage where you have memory layouts and stuff like that. Like this is the waffle compiler stage. I want to leave that as is. Just in conversion to bytecode, this is where I want to introduce tail calls, which means all the changes that I'm going to do, they will be contained in this something to the bytecode, to the ground bytecode. Here, waffle to ground. Yeah, this is where I want changes to happen. By eliminating tail calls. So how does that work currently? We compile the entry point function, then all other functions, then we patch function addresses. Fair enough. So compiling a function compiles the body, and afterwards the stack contains the return value. So what does a body do? A body compiles all the local functions. Then it compiles the return expression. Yeah, and then it pops the thing below the top. All right, let's I think in the body we can't generally do tail call elimination, because that's something that only works on the levels of functions. So in a function, if that return value of this body right here, if that return value is a function call, then we want to handle things differently. But then again, in this case, here's the return thing. Oh, actually, let's look at that in here. Yeah. Here, the last expression isn't actually a function call. The last expression is a switch. And then within this case, the last expression is a function call. Well, so yeah, that's kind of difficult. So I basically want to traverse into expressions, kind of. What if there was something like compile last of function, something like that, What if I took this compile expression of a body and this compile of a single expression, I'll just copy that, put that down here, And we can always merge similarities later on, but first I want to have the freedom of changing this however I like. So I want to call this compile last, and this is gonna the individual locals within a body, they are just normally compiled, but the body return expression we will do compile last. Yeah, then in here we do something after that. That's oh yeah, I think compile last needs the number of locals. Yeah. So that it can kind of clean up the stack before making a tail call. So here we can say locals size instead of doing that down there. Yeah, and then this needs that as well. All right. So then let's this is responsible for clearing the locals, which means that this run right here is responsible for removing the locals. So if we just have the parameter here, then we do something. If we just want to have padding, then we want to, oh actually this is, this is also becoming simpler, I think. If the last expression of something is padding, then we don't need to push the padding and then pop the locals before that. We can just first pop the locals and then push the padding. Oh, that's quite cool. All right, then in here we have a local expression. Yeah, here we can't pop the locals before that. So we need that, and then afterwards popping that. Although, we can kind of pop the stuff after the local and before. Yeah, that can be, we can make that better, but Yeah, the switch is the interesting part. Here we compile the byte of the switch, and then we create a jump table. And then within these, hang on, table.push. Yeah, here we compile the case, and let's turn that into a compile last. Yeah. The question is, do we still want a return after that? Not really. I'm wondering, does it... Maybe it makes sense to actually special case tail calls in the waffle. You know, kind of walk the waffle from the back, maybe. See, oh, this is a switch, so let's, you know, let's make this into a tail call, and then treat that like a diverging body in the rest of the code. Maybe that makes sense. But it does need, like, it kind of needs to free the other locals. So we do need to special case that in here, which is kind of unfortunate. Yeah, and the thing is, a call would then become, you know, a jump. But only if the padding is zero. That is weird. I'm not sure about that. Yeah, let me take a break. Alright, hi. So I think I'll actually just try to merge these functions, compile and compile last, by adding an extra parameter here that tells this, is this the last function, basically. Or the last expression. And we have that on both the body and the expression. Yeah, and then here we can do just compile of the builder with true. And then the idea is that this can, can do an early return. Like if there's a cast, a call as the last expression, we can instead emit a jump. And then, that basically is treated like a crash. Here I just need to adjust that. So these locals in a body, they are never, the last expression is last of the function. Maybe that is like a better name for that. I don't know. Actually, let's just call this like allow tail call or something. Well, I don't know. I think that's fine. Yeah, this is the last body in the function because it's the only body. And then in here we compile the individual expressions, the return expression. We compile that not with true, but with is last. This is the last body in the function, then that body's return value, that will be the return value of the entire function. That makes sense. And then here we have, some stuff. For aggregates, the last one will actually be the I mean, there are ways to improve that. There are ways to call this with a true sometimes, if this is actually the last expression in the aggregate. But for now, we can just be quite conservative and say we pass false in there all the time. indent that here. Yeah, like that. Mm-hmm. Do we call compile last at some point? No, we just call compile with true. Let's try that out. Is this in 117? Indeed. This should be that. Right, that seems to compile at least. And it runs, yeah, but this is the bytecode. And hang on, so we have this square root recursive function that in the one case it calls itself recursively. Yeah. So that's what we wanted to fix. I think that began here after the return instruction number 6. Okay, so it calculates some stuff, the condition, compares some numbers, and then it does this jump table, where the first case just jumps here, which adds 1 to something, and then jumps probably outside of the switch down here and returns. The second case, again, this equality, this is greater. If the square root candidate is greater than the square root, we are also done. We found the square root, so this would also jump here and return, jump down here and return. In this case, though, the candidate is less than the square root, or that the candidate squared is less than the square root. So we would jump here. Yeah, and you can see that we basically increment the candidate, and then we call this, we call ourselves recursively. Afterwards, we jump down out of the switch. So what I want to happen is, I want this to instead jump directly to instruction number 6 in here, and clean up the stack before that. And that means kind of tracing this down into these functions. So what kind of expressions do we have here? We have, first of all, the function itself. Within the function, we have, we pass in true here for the function body. The function body in our case has local variables, fair enough, and then it has a return expression where we kind of pass on this is last in fun. And this one then, hang on. Here we have a switch, which is, where's the switch? Here. All right, so we compile the switch condition with false. I see. Okay, so basically we want to pass in is last in fun here. Because the switch branches, they should be allowed to do tail calls themselves and directly return to their respective return value. And if they do, then we don't need to jump to the after the switch, basically. Yeah, that makes sense. The jump table index. Hang on, these get, yeah, they get updated here. Okay, yeah, let's try that out. Oh, I do think calls themselves don't use tail calls yet. Yeah, I kind of need to copy that from the compile last function down here. Let's see. So if we have a call, yeah, this one. All right, builder.align2 call.args.alignment. Let's just paste that in here and kind of diff that manually. So yeah, this is the same. All right. Then this one, the arguments, they are, yeah, we want to do something after the arguments. They are not the last, they are not allowed to do tail calls and stuff like that, because we want to do something with them. And then in here, we basically want to check if is last in fun and the padding is 0. Then instead of calling the function and popping stuff below the top like we do in here, we instead pop everything that's on the stack currently except the call argument size. So that would be builder dot stack size, I think. Stack size minus call.args.size. Skipping the top argument and popping everything below. And then instead of calling the function, we just jump there directly. Like that. I like that a lot. Alright, so this doesn't work for some reason because we probably need to make jump placeholder or something. Yeah. How do we aggregate these kind of patches? Patches is a list of patch. Well, that doesn't tell me anything. It's in here probably. Alright, patch what? And we have call and push indirect. We also want jump, I think. Jumping to a function. Yeah. And then, yes, similar to the call instruction, from call, we want a jump. Yeah, so rather than jumping or jumping with placeholder, we instead want to have a call to a signature. Yeah. Not sure about these. That's kind of weird. Anyways, what we do is we push a jump instruction. Jump instruction placeholder. Yeah, we don't do anything with the stack size, and then we could call like tail call. Oh, I think that's correct. That's amazing. That's crazy. Also like jump placeholder and patch jump they belong together. All right, and then in here we push a patch, which will be a jump patch to that signature, and then we just set the has crashed to true, similar to this. Yeah. Amazing. All right. Yeah, 144 in here. Instead we do tail jump. Not really tail call anymore. Actually, yeah, let's call it tail call. And it's actually a jump. Naming is difficult. In 26, here we also have a jump with some target. In which case we just jump there. Let's see. It works. At least it runs and returns stuff. Let's look at the bytecode. So here in the square root recursive function, we have a candidate and we have the target number that we want to take the square root of. And what we do is we push the candidate, we add 1, we push the candidate again, we push 1 to that again, we multiply them, so now we have the candidate squared. We push the actual target, we subtract them, compare them, so now we know whether the candidate squared is bigger than the square root. If it's equal, we do something, if it's greater, we do something else, if it's less, we do something else. We've looked at these before. Now let's see if it's less, then we do this. Alright, I like that. I think, actually I'm not sure, hang on. We've compared them. Okay, so now in the stack there is just the original stuff. So we add 1 to the candidate, and then this is the target. Okay, yeah, and then below those 16 bytes we pop the existing locals that we have. Sure. And then we jump to instruction number 6, directly up here to the beginning of this function. That's pretty cool. So basically our call of a call of a call of a call, etc. just was turned into a tight bytecode loop, essentially. That's cool. Yeah. And what's this stuff down here, though? We kind of pop stuff there and return, and that's not even reached, I think. Or is it? Oh, it is. I see. Oh, this is like after the switch. For the other cases, they jump to instruction 29, boom, in here, and that then pops stuff below the top. All right, I think that's tail calls actually. Let's clean that up a bit, and also kind of look at. It doesn't use tail calls in all cases. So there are cases where, for example, if you first of all, because we have this kind of general way of is just checking, is this the last expression in the function? We don't really have restrictions on which functions to which other functions can tail call. If you have a function foo that calls another function bar as its last expression, we just jump there directly. It's not just recursively calling the same function. And what we could do, for example, in something like here, is if you have a function that, I don't know, should calculate some point with an x and y coordinate. You have calculated the x coordinate, and then there's some other function that will calculate the y coordinate. You could just tail call that other function. That function will then just jump to that other function. That function will calculate the correct value, and then it will return, and will return directly to your own caller, which then expects the point to be there, which should work, So, yeah, for the last field of an aggregate, let's also do that. Let's say that for this we want to tail call that. Basically checking if that's the last field, right? So let's do like enumerate, I think. And then we have the actual item and then the index. And we can check if the index is aggregate.len. Then we will just do is last in fun, else false. Yeah, basically if if this is the last field in the aggregate and we are the last expression in the function, then we just pass that on and basically allowing tail calls in the last part of an aggregate. That seems reasonable. Okay, that's one of the changes I wanted to make. And the second one was, oh yeah, I noticed that this is called has crashed or something on the builder. I think it's better to call that like has diverged or something, you know. Because I mean, sure, crashes make the builder here invalid, but also tail calls that immediately jump into another function also make that invalid. So that's kind of a better name for that. Yeah. All right. This is weird, right? The fact that we have these has diverged things in here and then we just don't do anything. I think that's kind of weird. And in this case we disallow that. So I don't know how I feel about that. Anyways, I think that's fine for now. Let's kind of yeah, we need to fix that in here as well. Has crashed. There is going to be has diverged. All right. Okay. Yeah. I think that's fine. We have tight tail calls in here that just jump directly to the beginning of other functions instead of calling them and then immediately returning afterwards. Clean. Let's commit that. This is plum in here. This no. Hang on, this first the builder, I guess. Yeah, we have patch what with has diverged in several places. Plus we have the tail call function on that. Beautiful. And this makes more sense. Tail call sets has diverged to true. So then here we do that. We carry around this extra parameter for is last in fun. All right, I'm happy with that. Oh, hang on. All right, in the optimization, I kind of I did that off, without recording that. Fixing constant folding for addition, subtraction, multiplication. Division not yet because it can fail. I didn't want to get into that. But yeah, there are some, some low-hanging fruit for optimizations, I think, still left untapped. All right, but for now, implement tail call optimization, or sometimes how that's called is tail call elimination. Otherwise, I mean, it does replace that with something, it doesn't just eliminate that. Yeah, tail call optimization. There's a fine name for that. And with that, that's it for this time. And see you in another one. Bye.